Hello, class. This will be the last of the recorded lectures for section 2.4, and we're going to focus on graphs of secant and cosecant. Again, not in the grand scheme of things, not anywhere near as important as sine and cosine, but interesting mathematical approach to these. So what we'll focus on, let's do the cosecant. And secant is exactly the same, except instead of having sine in the denominator, you have cosine. And so you can see our definitions here. And what we have here is a nice graph. The blue is y equals sine of x. And remember, cosecant is 1 over that, and that would be the red here. We have the cosecant in red. And so when we talk about this, there's a couple things to think about. First thing is those asymptotes. So we have cosecant of x is 1 over sine of x. And the asymptotes occur when sine of x equals 0, right? Because we can't divide by 0. And so the idea is 0 pi 2 pi, or if we go negative, it'd be minus pi minus 2 pi. Second thing to think about is what happens to both these functions at given angles, right? So we have x, and let's define sine of x and cosecant of x. So what ends up happening? Well, let's just throw in a couple. So when x equals 0, sine equals 0, this is undefined, and so that's where one of our asymptotes show up. And what happens, say, at 90? Well, sine of 90 is 1. Always get your trusty sheet out here. And what ends up happening with cosecant? Well, what's 1 divided by 1? That's also 1. It's the only time where both of those points coincide with one another and they're equal. So let's just pick a couple more numbers just to see what happens. So let's pick one, say 30 degrees. Pick 30 degrees because sine of 30 is 1/2. And again, the math is pretty easy here because what is 1 over 1/2? Flip the fraction, it would be 2. So you could see that because sine of x, the biggest number is 1, you'll see that cosecant of x, the smallest number is 1 because you flip them. And when you flip a number between 0 and 1, you see it always gets bigger than 1. And so that's what ends up happening. And you see that these cosecant and the secant as well go up into infinities and negative infinities down at the other end of the spectrum. So let me just show you a couple other examples. Say like you pick the number 2 degrees. Well, what is 2 degrees sine-wise? Well, here you need your calculator. So sine of 2 degrees is 0.034. And if you take the inverse of that or flip that, you see you get 28.65. So you see how cosecant is blowing up in that direction, right? And on the other hand, it gets close to 1. What is 88 degrees? Well, 88 degrees sine-wise is 0.999 and some change. And if you flip that, you get 1.0006 and some change. And so you could see that as it gets closer to 90, it's going to get real close to 1, and the time where they're both equal is at 1. So hopefully this gives you a feel for what we mean by the inverses, right? You kind of flip those fractions. And again, a nice looking graph would look like what we have in the slide here. And so secant and cosecant have those same attributes that we want to talk about. We want to talk about the period, and we also want to talk about the phase shift. And with regards to those, it's again the period or the amplitude, excuse me, is not as important because when we talk about amplitude, when you multiply a number by infinity, it's still infinity. So the amplitude is just how quickly it blows up to positive infinity or goes down to negative infinity. So we really don't focus on amplitudes just with sine and cosine. One last thing I want to point out on the graph before we move on is where do these kind of graphs start? It's always a good thing. Like, remember we showed you where the sine and the cosine started, and then we talked about cotangent, tangent, where they start. In this case, where I think about where these graphs start is where these two intersect. So where is the lowest point of the secant or cosecant graph? And it always occurs when for example, cosecant's minimum is when sine is 1, and secant's minimum is when cosine is 1. And so when we talk about these phase shifts and periods, it's the same aspect of it. We give you an equation that looks like this. Y equals cosecant we'll put an A out here, but that doesn't matter. And then K, X minus B. And again, we don't really talk about the A very often, of the amplitude, excuse me, but we are worried about the period. And we're also worried about the phase shift. The phase shift is B. And in this case, again, the period's just like sine and cosine. It's 2 pi divided by K. So when we talk about moving these things a little bit, let's pick something here. And so let's take a look at this one. Y equals 1/2, which doesn't really matter. And then cosecant of 2 times x plus pi over 4. So let's just take a look at that one. So our K value in this case is 2. So our period is 2 pi over K. And so that would be pi. And our B value in this case is minus pi over 2. Remember, what you want to take the opposite is one way of thinking about it of B. Or what you plug in for x to make what's inside those parentheses 0. That's our phase shift. So in this case, our phase shift ends up being minus pi over 2. So what happens to our graph? Well, let's just take a look of a couple things, right? Number one, where did our graph start? Well, let's go in blue here. You remember this was minus pi, right? And this was pi. And so remember, wherever sine is 0, you had an asymptote. And so the other asymptote was, say, example, right at the y-axis where the angle equals 0. So what happens when we change the period? Well, just like in the tangent, we also will change where the asymptotes are. So if you think about it, if we change that in red, we're going to move the red one now to half that. So that would be pi over 2, still in here, and that at 0, because 0 is, and then we cut that in asymptote in half, and that would be minus pi over 2. So that would be the first move. So what does this minus pi over 4 mean? Well, that means, and let me do that one in green, is that we are shifting the everything by 45 degrees or minus pi over 4. So we're shifting that asymptote by pi over 4. So this would be pi over 4. We shift the 0 to minus pi over 4. And then we shift that one to minus 3 pi over 4. You could do the same going to the right as well. And so the last thing is, where is our start point? Well, with regards to our start point, remember that our start point occurs when sine of that value equals 1. So you're looking for what's inside of the argument for cosecant, where that's going to be, it occurs at 1 at 90 degrees, right? So, and that would be pi over 2 in radians. So how do we get pi over 2 in radians there? Well, let's think about that. You have this 2 out front, right? So what do you want? Pi over 2. So x would end up being 0. So actually, these things start right here. And so it would end up looking like that. And then when we get to pi over 2, you get down to minus 1, and it would look like that, and so on and so forth. Whoops, wrong way. So this one actually goes down. So this one would go down as well. And so you can see period changes, phase shift changes where we start. And so you change the asymptotes, and then you change the start point. And the way I think about the start point is the lowest value of cosecant or secant. So if you took a look at this graph, it would look like this. So you can see that ended up being a prettier version of what I tried to do. So that ends the recorded lectures for section 2.4. Again, in the grand scheme of things, nowhere near as important as a really good understanding of sine and cosine graphs, but a very interesting mathematical representations of the rest.